So we want to integrate sine over region in the first quadrant bounded by an ellipse. Have a look at the region. Okay, so we want to sketch this thing. We'll set y to be 0. It'll tell us about the x-intercept. So we'll get an x-intercept at a third. And then we'll set x to be 0. That'll give us the y-intercept. So we get a region like this. Bounded by an ellipse. Okay, we want to integrate something over this region. So it's not quite polar coordinates yet, right? In polar coordinates, we would need a circle. Here we've got something that's a little bit taller than it is wide. Okay. If we tried to do this directly, we'd wind up trying to integrate something involving something like this, right? That would be difficult to integrate. You know, you'd have to do some kind of trig substitution to be no good. So what we'll do is we'll do change of coordinates so that it becomes more circular, right? If we can account for the change in, if we can round this region out and account for the change in area, then we can do this in polar coordinates instead. So we'll make a move to polar coordinates. Or here, I'll write down that idea. Polar coordinates are nice, so we'll make that region into a circle. So what do we need to do to make this thing rounder? We need to do a linear transformation that'll make this into a circle. So we want these guys to actually be 1, 0, and 0, 1. Right, that would give us a nice round circle. Okay, so that applies the appropriate amount of stretching. So in UV coordinates, this thing is now beautiful and round and nice. Okay, so we'll do the coordinate switch for that. calculate out the Jacobian matrix. Okay, but everything is nice and linear here. The derivative of x with respect to u will be a third. And a half. Okay, so we take the determinant of that, plug it in here. So this has made things quite a bit nicer. Right now the constants on those variables have gone away. The problem is somehow much more symmetric than it was before, right? Here, the y-axis was special, the x-axis was special, and now we've gone to this, perfectly round, beautiful situation. Made things more symmetric and nice. Okay, so this would be hard to integrate, right? We've got sine of something squared, right? Usually you don't see that in a Calc 1 course, a sine of x to the 4. You wouldn't be able to do a u substitution or something. So what we'll do is we'll do another coordinate transformation to polar coordinates. Right here we've got this nice symmetric circular thing. Now we'll go to polar coordinates. So in polar coordinates, we're looking at our domain B star. So theta goes from 0 up to pi by 2. Radius goes from 0 to 1. Sine r squared. And the all-important Jacobian r d theta. And now this is some, oh, yes, question?
What about the 1/6?
Oh, yeah, what about the 1/6? Yeah, totally. Should still be there for sure. Yeah. Yeah, we're just working on the integral part. Yes?
Why is it r squared? Shouldn't it just be 1 squared?
Aha, right. So, just a quick refresher on polar coordinates. Right, so our x and y look like this, which means that these two guys square to r squared.
Right, we know for this, since it's a circle with radius 1, then r squared would be 1, right?
Aha, right, so that happens at the boundary. Yeah, that happens out here. Right, so that's where we get r is 1. But we need to integrate even down here, right? So r needs to grow. So this is theta is 0. Theta is pi by 2. R is 1. Nice. So now we get here and we go, aha, this is integrable, right? Sine of r squared is integrable. So we integrate sine of r squared. Here, right, the antiderivative of sine r squared times r would be negative a half cos r squared. So we make this one-dimensional change of coordinates. Now we plug in those bounds. Doesn't come up all that often, but cos of 1, interesting number. You'd hope that it's special, but it's like just cos of 1, not cos inverse, it's cos of 1. Okay. We get a sixth. Pi by 2.